Well, hopefully the MML server being down a little bit on Monday didn't affect any of you. It seems to be fine now, but I guess it's a little abnormal, but if it continues to happen, then we can talk about like shifting assignment due dates. Like I said, usually it's not an issue, but if it gets to be an issue where it affects people's ability to do homework and stuff, we can discuss, you know, like an extension on things. So don't worry about it too much. It'll all be okay. So are there any questions on the homework, 2.1 or 2.2? Yeah.
I'll bring them up. I think it was the last one on 2.2. I was trying to remember what little brackets around the X meant, the limitations.
This one?
I think that was just a really poor way of being parentheses.
Yeah, so that's the notation of the function. It's the greatest integer function. Sometimes it has like double bars on both sides. So really, if you forgot that function, which you probably did, it's not terribly common. It's just, you know, like taking the sign of x or the absolute value of x. It's just that particular notation to say take the greatest integer that's less than or equal to the thing you plug in. So that's what those, you know, L's mean. Okay. But in order to answer the limit, the graph is provided. So in 2.2, we're still kind of looking at limits graphically. So, but that's what the brackets mean. It's just the function's name. So, yeah. Any other questions on the homework? So, yeah, we're still in 2.3, and we looked at this particular example in one of two ways, or two ways rather. One, the conjugate method, which is the general approach typically when you have radicals involved and you're trying to simplify expressions involving radicals. And then we looked at maybe a little bit more efficient way to factor, which doesn't always work. It really just depends on the expression. So let's note that here, that this does not always work. And we'll see an example after this in a moment where we can't factor. We have to use a different method to simplify. Okay. As a reminder again, if your function is undefined at the location that x is approaching, but you do get a limit in return, like 1/2, then that's going to indicate you have a hole on your graph at that x value you're approaching, comma, the limit value you obtained. So we said x is approaching 1, y was approaching 1/2. So that means we have a hole because the original function is undefined at 1. Because when we plug 1 into our original function, it causes us to divide by 0. Okay, so undefined at 1, y value of 1/2, you have a hole at 1/1/2. Okay, did anyone have any questions on that? That's not just true for this example. We wrote it down explicitly. For any function, you approach a finite number and you get a finite number as the limit. If that value of x is not in the domain of the function, you will have a hole on your graph. So it's not that we graph a lot of things. I just think it's important to know, like, not only how to compute a limit, but what that's actually telling you. It's giving you information. So what kind of information is it giving you? That's, to me, is equally important as just being able to compute a limit. Okay. So this is another example. Quite similar to the previous one. So we could either involve the conjugate of the numerator, and again, the conjugate's there to get rid of the radical portion. So we would want to conjugate the numerator and then multiply the top and bottom by the square root of x plus 3. Or we could just say, well, this is kind of a similar situation. The x minus 9 is the issue, because it's giving us a 0 in the denominator. But if we view x minus 9 as a difference of squares, we can say that's the square root of x plus 3 times the square root of x minus 3. Oops, sorry. Times the square root of x minus 3. And then we can immediately see that that will eliminate with that factor up top. So really the point of showing you the two different methods is, you don't necessarily have to factor these. You can always get through the conjugate method. But when you can do this, it's a lot more efficient. So we have that simplifying to the limit as x approaches 1 over the square root of x plus 3. And so what would that limit be?
1 over 6.
1 over 6, because we're going to plug 9 into the root. 1 over the square root of 9 plus 3 is 1/6. So on this graph, which we see just a portion of it, what's happening? What does that limit tell us? There's a hole at
9, 1/6.
9. X is approaching 9. So there's a hole at this x value. 1/6 is our y value. So I don't know. Let's see. That's 1 over 6. And if you're using that particular software, it's not going to say that it's 9 comma undefined until you actually hover over that point. But saying it's 9 undefined isn't specific. Like, because that could, where is that y value? Is it all the way up here? Is it down here? When we compute this limit, we know exactly where it's at. All right. So are there any questions about those two examples? All right. And so I guess the pattern that we're looking at with these two is that we can, if we have like x minus a, we can factor that as the square root of x minus a. Sorry. That's not right. Well, I can leave that. I'll just change this. X minus a squared, like in this one here, x minus 9, or the previous example, x minus 1. That we can factor it root x minus a times root x plus a. But again, that's not always the case, right? Like x minus a squared is very specific. All right. So an example of where that wouldn't work would be this example here. So these next two examples are sort of here to remind us of certain, simplification processes that might have been forgotten or tucked away and not easily accessed. So remember, the first thing we do when we evaluate any limit is to do what?
Plug it in. Attempt
Yeah.
direct substitution.
Yeah, we'll just attempt directly substituting in this value. So I'll just denote this, when we directly substitute, if it works out to something we compute, then that's fine, we're done. There's nothing to do with that limit, we've already computed it. But we do see that the bottom is going to be an issue, right? It really, at this point, it doesn't matter what the numerator is. Overall, it does, because once we get into chapter 4, we'll start to see that limits that take on particular forms, we can tackle them in a different way. Okay. So just so we're sure, what does the numerator evaluate to when we directly substitute our limit as h approaches 0?
Zero.
0, right? Because we have the square root of 196 minus 14, which is 14 minus 14. Okay. So again, the issue is that 0 in the denominator. I guess it doesn't. Oh well, I'll just write it again. All right, so then we have to try to simplify this algebraically. And so what would we do algebraically to our expression? Square root of 196 plus h minus 14 all over h. Multiply by, sorry?
By the reciprocal.
The reciprocal. So if we multiply this by the reciprocal, is that going to help us?
The conjugate, I'm sorry.
Yeah.
Conjugate,
Yeah, yeah.
that's the word I was looking for.
Okay.
Yeah.
So yeah, if you're thinking reciprocal, then like algebraically that's not equivalent. If I multiply something by its reciprocal, I'm changing its value, right? So if I multiply any of these expressions by something that's not 1, then I'm changing the thing and I'm making up a new limit problem. So the conjugate of the numerator is the square root of 196 plus h. What else?
Plus 14.
Plus 14. And so if I want to multiply the numerator by this thing, and again, the conjugate is, you're invoking the properties of the difference of squares, is the reason the conjugate's introduced. So if I do that at top, I want to do the same thing on the bottom, as to not change the value of my expression. Yeah.
This might be a silly question, but for conjugate problems, does it matter if they're, obviously we do plus 14, but let's say the 14 wasn't there at all and it was just the square root. Would there be a different process of doing that, or is it just same thing, just there's no 14 now?
Yeah, so if there isn't a 14 here, is that what you mean? Like
Yeah.
if it was just that? So yeah, if it was just that, then we would just multiply by this.
Okay.
So it wouldn't be negative square root.
Do what?
It wouldn't be negative square root 196 plus h.
No,
It's
wouldn't.
just the same.
Not a negative. That first term stays the same. Again, the property we're utilizing here is, I don't know, take like n plus m. If that's one of your expressions, then we're going to multiply that by n, left that alone, minus m. So we just change the sign on that second term, whether it's on the, they're conjugates of each other. So again, what that does up top is now we have this thing, let's just call that the square root of all of that stuff a. This is still a, we didn't change the sign, minus b for the first one here, and then this is plus b. So really what that's, kind of simplifying to, if you want to look at it that way, is we're just taking a minus b, multiplying it by a plus b. If that doesn't really make a lot of sense to you, then just multiply the stuff out, you FOIL it, or you do the, the box multiplication method, however you do those things.
These ones I found it's really helpful to throw those parentheses on, just
Yeah.
to keep everything straight.
Yeah, right. And so a lot of times people will just like multiply a couple of these things together instead of multiplying it out fully. But you are multiplying all of this times all of this. Okay. So we know when we multiply the top, that it's just going to be a squared minus b squared. So if this root 196 plus h is our a, and we multiply those two things together, then that's where the benefit of the conjugate comes in, is because that just eliminates the radical on that first term. The, what is it, FOI, outer and inner? Who uses FOIL? I just want to make sure that we're, So yeah, the outer and the inner terms will cancel because they're opposite in sign. And then you have negative 14 times positive 14, which is minus 196. So that's what's left over up top. Still the limit as h approaches 0. And like we saw in those other examples, the issue that's giving us a 0 in the denominator, we don't want to multiply that through everything because then it's kind of lost. So this was our issue. We want to leave it there as it is so we can get rid of it. But it's still multiplied by all of this stuff. Root 196 plus h plus 14. We'll just leave that as it is. Is everyone clear on that? Does that make sense why? Yeah.
How would our answer be different if in the original equation that we were given it was plus 14 instead of minus 14?
So if we started off with the root 196 plus h plus 14,
Yeah.
then what we would have multiplied top and bottom by is root 196 plus h minus 14. So then this part right here would have been a minus. We would have still received the same result up top, and this would have been a minus. So that would be the only difference. Okay, let's combine up top, and then we see that our 196s are canceling out. So we just have an h up top over this h times our root 196 plus h plus 14. Okay, now the issue of dividing through by h approaching 0 really in the bottom is getting canceled out here. So we are eliminating, oops, we're a little too large. We are eliminating the issue that we had originally. Okay, so it simplifies to 1 over root 196 plus h plus 14.
The reason for that is, well, because you put 1, so essentially, I mean, as like common sense, not common sense, but there's a 1 in front of the h.
Right, yeah, you can view it that way. We have this 1 here. Oops. This 1 right here times this h, and these h's are dividing out. So what's the limit?
1 over 28.
Yeah. So we're just, now h is going to 0. We said, well, we did this algebraic thing, and then I simplified it. Let me try to reevaluate the limit. So then I'm just going to plug that 0 back in for h. And so I have 1 over the square root of 196 plus 0 plus 14, which is 1 over square root of 196 plus 14, which is 1 over 14 plus 14.
Can you have like a conjugated reciprocal? Is that even something that is used or a defined term mathematically?
Yeah. Yeah.
Okay.
I don't recall a situation where I've needed to use that.
Is that essentially what that is though? It's a conjugated reciprocal?
Well,
Before you substitute 0.
yeah, so like this stage right here.
Right.
Yeah.
Right there.
I mean, I wouldn't necessarily just label it as a conjugated reciprocal of the original, because the reciprocal of the original is h over,
Oh, that's
right?
true.
So,
Yeah. That's what you're saying.
yeah. A lot of times you got to be careful, unless it's presented like as a theorem or a fact or a definition. There's many instances where we do like a couple of problems and we're like, oh, hey, this seems to follow this pattern. Like if you want to work then with the generic or the general version of that to see if there is a pattern that emerges from that, like multiplying x minus 3 times x plus 3 and seeing that that's a difference of squares, then that's fine. But we want to be careful with, just doing one or two examples and saying, oh, this is a definite pattern, and I'll always use this way, because it's not usually the case. So I know it's really tempting to look for shortcuts and patterns when we do certain things, but really what we want to focus on are the methods as opposed to the results, I guess. Okay. So are there any other questions on that example 3? Okay, so that was one strategy we had sort of from algebra or pre-calc. The other one involves complicated or complex fractions, where you have like fractions within fractions. So again, a lot of these limits are simply algebraic processes, like how do I simplify this particular expression? Again, evaluating this directly, we'll end up dividing through by 0, which, as we've seen many times in the sense of a limit, that doesn't necessarily mean that it doesn't exist, right? So when that particular thing happens, direct substitution, I'm going to scoot this over. When that particular thing happens, it's not a reason to just stop and say there is no limit. Okay. So the process of simplifying like fractions within fractions, what do we do with those?
We have to find the least common denominator and do those fractions together.
Right. So in essence, what we have to do is we have to combine the top. So like, let's say we combine the top and it's like, something over something else. And then we have that over h. Then we can simplify that into a single fraction. Like that. And we don't have fractions within fractions anymore. But it does involve combining those two things, whether they're added or subtracted together. So really there's two approaches we could take. It's like, well, what do I need here in each term in the numerator to add those two together? Or I could just clear those fractions in the numerator completely. And I think if you clear the fractions in the numerator completely first, that it's easier, because then you don't have to deal with another fraction within a fraction. But either method works. Do this. So when you see this type of stuff, then look at these two denominators here and say, what's the lowest common denominator? Let me put this over here.
Plus 9h.
81, yeah, right. If you multiplied it out, 81 plus 9h.
You could just do 9 times 9 plus h.
Yeah, I think a lot of there's a whole lot of emphasis in algebra put on the lowest common denominator, and I guess it really depends on who your teacher is or who you're talking to. But in my opinion, the only advantage of finding the lowest common denominator is so that you don't have to simplify when you're done. If you find a common denominator, and you just have to simplify after you're done. So a lot of times it's easier just to find a common denominator. And even if you have all of these redundant factors, once you kind of go through the process, you'll see all of those things canceling out anyways. So if it hurts your head to look at like complicated denominators and think about, well, I should factor these things and then look for the lowest possible common denominator that they all share, then don't even think about that. Just take all of their denominators and multiply them together, because that will be a common denominator. So if I just take the 9 plus h as denominator number 1 and multiply it by the other denominator, then, in this case it is the lowest common, but that would give me something to work with. If it's not the lowest, then we'll have to just simplify what we have on top, but I think it's easier just to think of it that way. Just take the factor denominators and just multiply them all together. Okay. So remember the purpose of the LCD or a common denominator is to get rid of, maybe we'll call these the smaller fractions up top. So what do I have to do with the LCD in order to obtain that result?
Distributed?
Yeah, to where?
Both the numerator and the denominator.
Yeah, both the numerator and the denominator. Again, I don't want to change my expression, so I have to multiply this by 1 in the form of 9 plus h times 9 over 9 plus h times 9. So, let's kind of go off to the side here. And look at that algebraically. Because what we're doing is we're saying we're taking 8 over 9 plus h minus 8 over 9. And we're multiplying that by 9 plus h times 9. Over 1. So we're distributing both of these, or this factor, into here and here. And so what do we get when we do that? So we can write it out explicitly. So we have the 8 over 9 plus h times 9 plus h times 9. So what would that give us?
72.
Yeah, because the 9 plus h cancels out. We just have 8 times 9 up top. So that's 72. And then similar thing here, we have 8 over 9. Multiplied by 9 plus h times 9 over 1. So what does that give us?
Just 8 times 9 plus h.
Yeah, so it just gives us this. Oops. 8 times the quantity 9 plus h. All right, so that's the numerator. That's the entire numerator in that expression above, but it doesn't have any more fractions. If you wanted to just subtract those two things from each other, then you've got a pretty similar process. And let's see if this will simplify further. We've got 72 minus 8 times 9 is 72, minus 8 times 8h. So it looks like it simplifies to just minus 8h. And let me write this here. Minus 8h. Okay. Any questions on that?
Just cross multiply?
Hmm?
You just cross multiply?
From where at? From the start here?
Yep.
Yeah, so if you cross multiply, what would you get?
Negative 8h.
Okay, so how are you cross multiplying these two things by this thing?
I'm multiplying 9 plus h by negative 8 and 8 times negative 9 and then add it all together.
So you're multiplying minus h times 9 plus h? Sorry, say that again.
That 9 plus h times negative 8.
Uh-huh.
So you get negative 72 and negative
8h, yeah. Uh-huh.
And then you get negative 72 when you multiply 8 times negative 9. And you're just left with negative 8h.
But wouldn't it be positive 8 times positive 9 to give you that positive 72? You wouldn't have the two, you wouldn't have negative 72 and negative 72, right? The negative 72 came from this negative 8.
Well, yeah, I only use the negative ones because if you use it
Okay.
both times,
Yeah, I mean, it's, you get the same result. I would just say be careful. If you're okay with that process, then, you know, again, it's a shortcut. But this is actually what you're doing, kind of skipping some steps. But if you're able to get these answers, then I don't see anything wrong with that. Just be careful. All right, so I just chose to simplify this stuff. What was this times this? Negative 8h, right? Like I said the last time or last class, you can just sort of keep the limit in there and just simplify as you go, or simplify the expression first and then start working with the limit again. But at some point you need the limit in there to indicate what you're actually doing. So you have a negative 8h on top is what all of that stuff simplified to. Again, the issue on the bottom was this factor of h, so we'll leave it factored. And then we see, as in the other examples, the issue of the 0 on the denominator is now we're able to divide that out by a factor in the numerator. So this simplifies to the limit as h approaches 0 of just negative 8 over 9 plus h times 9. And we say, all right, well, we did this algebra trick. We simplified it as much as we can. The problem went away. So then we reevaluate the limit. As h approaches 0, what is this limit equal to? Negative 8 over 81. Yeah.
So when you get to this stuff, you just plug in 0 for all the h's?
Correct.
So why wouldn't the 8h be 0?
Because this h and this h canceled out.
Oh, so it's 1.
Yeah, any other? Yeah.
So let's say we're writing this on a test. Would we have to rewrite the limit as h approaches 0 equals negative 8 over 81? Or is just what you did there?
No, this is fine because what you have is, it's reading like this. This limit is equivalent to this, which is equivalent to this, which is equivalent to this.
Okay.
But, the issue I see on exams is people say, like negative 8 over 9 plus h. So they'll like totally simplify everything correctly, algebraically. And then they'll just say, this is negative 8 over 81. And so clearly that is a false statement. The only way all of this stuff is negative 8 over 81 is if the limit as h approaches 0 is attached to all of this stuff. So don't drop that notation. Even though you're working with this, and even though h is going to 0, you need to have this notation here, because anybody else that looks at that is going to say, if that limit's not there, that makes absolutely no sense whatsoever. It's just proper notation, especially if you're going to continue on in math. It's crucial that you're using the correct notation. Yeah.
So I think everything's pretty clear so far, except for the part where we got negative 8h. I'm not sure how we got to that.
This part here in the box,
Yeah.
how we got to negative 8h.
Right.
Okay, so we said that we looked at the original limit and said that since we have this, these smaller fractions within a larger fraction, that the procedure is to take the denominators here of the smaller fractions and multiply them together. So that's how we generated the 9 plus h times 9.
Right.
And then we have to multiply top and bottom so we don't change this expression. All we did here in this box off to the side was we just simply multiplied the numerator out. So the 9 plus h times 9 had to be distributed to both terms in the numerator. So here's the 9 plus h times 9 distributed to this 8 over 9 plus h. well, times 1, because we had this over 1, right? And then here, the second part is the 9 plus h times 9 over 1 times the negative 8/9.
All right, I see.
Okay, yeah. Is everyone all right with that? And it's probably this kind of tucked away algebra thing that you haven't used in a while, but definitely you'll utilize it. Any other questions on that example? Honestly, I hesitate to say this, but it's almost like calculus is 80% algebra and trig, and the other 20% is like what to do with the calculus stuff. Okay, I think that's it. Yeah, and so like if you recognize the structure of these two expressions in our limits, then you might recognize that, well, that was when I was dealing with the h in the denominator and all of that stuff, and that was the difference quotient. Do y'all remember that? So when they said, in pre-calc, when it said find and simplify the difference quotient, you found and simplified the difference quotient, and you ended up with something like this, and that was your result. You just stopped there. There was really no context to it other than the difference quotient. If we look at it as f of x plus h minus f of x all over h, what is that? What is the difference quotient in general? A slope, right? It's just the slope between 2 points. So this is kind of how it's structured. You said, all right, well, here's f of x, here's an x value, and here's a x plus h value. And so what is f of x? Well, I know it's right here. What is f of x plus h? It's right here. I put those two close together. But then notice what we're computing here with the difference quotient. It's the change in the y-coordinate divided by the change in the x-coordinate. So you're just calculating the slope of that line connecting those 2 points. It's not really flat. I did a poor job. But the difference quotient is, just as a reminder, the difference quotient is the same thing as the average rate of change, which is the same thing as computing the slope of a secant line. And so if we compute a slope and say, all right, this is my difference quotient, then that just gave us the slope of the secant line. But from 2.1, we said, if I insert a limit on the slope of my secant line, what does that turn into once I compute that limit?
Slope of the tangent line.
The slope of the tangent line, right. So it's only once I insert this limit on the difference quotient that I get the slope of the tangent line. And that's one of the main pillars of calculus, is how do we find or compute slopes of tangent lines. So this thing we'll see later is called a derivative, and that shows up in chapter 3. But as far as computing a derivative for a lot of different functions, you already know like how to get there because you found and simplified the difference quotient. The only modification we need to make is to find the slope at a single point, is then to introduce that limit, and then now you're doing calculus. So hopefully you remember that. You might not have done a lot of it, but that was kind of the point. Any questions on that stuff? So at least through these this first unit, I hope that you can find somehow to tie it back to like your prior learning, because most of this stuff you really have done already. There are some new stuff, there's some new material, but even in the next two sections, 2.4 and 2.5, you've already done that stuff. You just looked at it through one window, and we're going to take it and look at it through a different window. Okay, another method. So these are particularly helpful in evaluating, or what we're building towards anyways, is particularly helpful in evaluating, more kind of elaborate type functions. So if you were asked to compute the limit as x approaches 0 for cosine 1 over x times x squared, then let's just see what happens if I directly substitute. I get 0 times the cosine of, and we might say, well, it's 0 times whatever, so it's always 0, right? But no, because cosine 1 over x is really the cosine of 1 over 0. And so you have 0 times something that's not defined or doesn't exist. So, I mean, we'll write that here like this. It's 0 times something that does not exist. So you really can't make sense of it. Like, it's not 0 times 5, which is 0. And then so we would say, all right, well, there's a definite issue with that function. Is there anything I can do to simplify x squared times cosine 1 over x? We can't factor anything. We can't rationalize or simplify the fraction within the cosine. So the methods we've looked at so far are limiting in some regards, but by and large, they do tackle the majority of limits that we see, but they are limited. So we've got to talk about another way to compute certain limits, like this one, for example. And so we'll start off maybe with a numerical statement. So what if you say what if, I'm thinking of a number. Right now it could be anything. There's an infinite amount of choices for that number to be. But what if I told you that the number I'm thinking of, let's call it n, is smaller than or equal to 10 and larger than or equal to 10? What number am I thinking of?
10.
Does everybody agree? This seems pretty straightforward when we put it in a numerical context. But the number has to be 10. So what we're going to do is we're going to take the same sort of numerical statement, but we're going to put that into context of functions. So we'll, maybe that's question 1, and then we'll say question 2 is, we'll just write it out. I have a function that I'm going to call g of x, and g of x is going to be smaller than or equal to h of x, but larger than or equal to f of x. And this statement holds for all x. We might have to modify that slightly, but we're just trying to get the basic idea. Okay. So I always know that the function g of x, the y values are between the function values f and the function values of h. So if I know that's true, and then I said, all right, well, let's compute the limit as x approaches a on all of these functions. So x is approaching just some random number. Do you think it's true that this inequality still holds? Does that make sense that it would still hold? If g is always in between f and h for any x value, it doesn't matter what x value I approach, it's still in between those two functions. Can everyone agree on that? So that's the main idea of the squeeze theorem, where what we're dealing with is, let's just say for argument, and say we know the limit as x approaches a on f of x is equal to the limit as x approaches a on h of x. Let's say we know that limit. I don't know, let's call it L, just to keep with our limit notation. But just some finite number. And say we knew that as a fact. So the question now is, what is the limit as x approaches a on the function g of x? Does everybody see that it has to be L? So we'll rewrite this again. We're saying that L, the limit as x approaches a of f of x, is less than the limit as x approaches a on g of x is less than or equal to L. So this limit that I need to compute, I know is in between, or sorry, less than or equal to L, but greater than or equal to L, which means it has to be equal to L. So just kind of look at it down here. And so that's the squeeze theorem for functions. It helps us compute limits in that way. We squeeze or sandwich, sometimes called the sandwich theorem. You squeeze or sandwich a difficult limit in between two well-behaved limits, and hopefully that the two ends, the limit on f and h, hopefully they're the same thing, because then you've squeezed your limit in between a particular number, which means your limit has to also be that particular number. So that's what that theorem says. The modification we made here is that f, g, and h satisfy that inequality for all values of x that are near a, except possibly right at a. Again, that's just based on the limit. Doesn't care what's happening right at that x value. Okay. So if I know my two limits here on the end are equal to something, then the limit on this function has to also be equal to L. So this function is in between those two numbers. So really, you know how this kind of evolves in practice. We'll write this again. These two limits here that are sort of on the end, if you will, those should be the easier limits. And I'll just put that in quotations because it's, you know, it's a relative term. The limit in the middle is the one you're trying to answer. So that limit stuck in the middle here is the difficult limit. So to answer the question about the difficult limit, we're hopefully just answering a question about the two easier limits on the outside. Do y'all have any questions about that? All right, with that in mind, then we'll go back to the function x squared cosine 1 over x. Does everyone have what they need? Move on. Can't simplify, can't rationalize. You know, I don't. We might think of an identity, but no identity is going to help us here with this 1 over x part. So then we would say, all right, well, can I take my function? This is like my g of x now. If you're referencing the previous theorem. So can I take that particular function and put it in between two, you know, quote, easier functions to compute limits on? What do we know about the cosine of an argument? Can we bound that? Think about the graph of cosine. What do we know about it? It's between 1 and -1, right? So remember when you saw this cosine of x is in between 1 and -1, well, that x could be anything. It's, you know, if that's in between 1 and -1, then so is this. It'll look a little bit different, of course, because you've got a different argument. However, the cosine is always in between 1 and -1, so that's a good starting spot. It's not always the best spot to start with. So I will say that if you have to utilize the squeeze theorem on the exam, the inequality or the relationship between the three functions will already be provided. Like, I'm not going to expect you to justify this function's in between these two functions, because that gets really, really difficult. Because a lot of it isn't even intuitive. When you see some of these in the textbook, it's like, well, how do they know to put that in between, like, the absolute value of x and 1 minus x squared? It's really not intuitive to set a lot of these up. So the inequality that you need to use the squeeze theorem on the exam would already be provided. So don't worry about coming up with an inequality all on your own. Okay. All right, so we know that is a fact for cosine of 1 over x, but what we want to do is we want this thing here, we want that to be g of x. It's not quite g of x because g of x has that x squared multiplied. But to fix that, we're just going to multiply through everything that we see. We're just going to multiply through by x squared. So then we have our negative x squared is less than or equal to, x squared times cosine 1 over x is less than or equal to a positive x squared. Is everyone all right with that? Yeah.
So let's say we had the square root of x instead of x squared, would we do the same thing?
Yes. So like if it were root x cosine 1 over x, then from this point here, we would just multiply through by root x. So we're just trying to figure out what can we multiply or divide or add to everything so that this can look like the actual function that we're dealing with.
Oh.
So are there any other questions about that? It's kind of weird at first.
So if like x was approaching, if x was approaching like maybe a positive number, like 4 or 5, say it's 5,
Okay.
would it be, would your left and right hand values be 4 and 6, 1 plus, 1 minus?
It really depends on what function you're dealing with, right?
Okay.
Are you specifically talking about this one here?
Yeah, I guess just say, for example, like it's,
Yeah, well, so if we're talking about this one and x is approaching 5, then I don't have to go through any of this because I can just plug 5 in. It's 25 times cosine of 1 over 5, well, and that'll give me a specific value.
So is the squeeze theorem generally used when you're attempting to divide by 0? Most commonly, I guess, if 0 is going to be sitting in that denominator?
Not always, because technically, I mean, yeah, a lot of times, but not always. Because technically here, we're not dividing by 0. Like, we don't have a denominator for this function. We have a denominator for the argument of cosine. But this is still, x squared times cosine. So it's still a function times another function. So it's really not that we're dividing through by 0.
Okay.
It's in the argument of cosine where we're dividing through by 0, which gives us the issue. Not that we're dividing everything through by 0.
Okay.
I don't know if that helps or not, but it really just depends on the situation. Like if you can simplify it algebraically and go ahead and do that, if you can't, then you might want to try to use the squeeze theorem. But it'll be very clear since we're just first starting out with this. Like the homework will say, use the squeeze theorem to do this, right?
We use this when we are dealing with those ones that just oscillate off into perpetuity.
Yeah.
Just we're trying to trap it.
Right, right. So, yeah, that's by and large, we see the squeeze theorem when we're dealing with sine or cosine, typically, because they're doing this forever.
Right.
They don't flatten out.
Right.
So what we're trying to do is just bind them in between something that's more well behaved. But yeah, it'll say use the squeeze theorem, so you'll know. Because otherwise, it can be kind of ambiguous.
Isolation, asymptotes.
Yeah, right. You're almost saying like this function is like asymptotic to these two functions.
Gotcha.
Yeah. Okay, so once you have this, or if you're given this inequality that's established, then again, the question we're trying to answer is what is the limit as x approaches 0 on this middle piece here? So then naturally we need to insert that. So if this is true, then what we have is the limit as x approaches 0 on negative x squared is less than or equal to the limit as x approaches 0 on x squared cosine 1 over x is less than or equal to the limit as x approaches 0 on x squared. So that's really all you have to do if you're given that inequality. And then hope that it boils down to something that's meaningful. So what is the limit as x approaches 0 on negative x squared? 0. Less than or equal to, we're unsure of this limit, we're working with that one, so we're just going to leave it as it is. And the limit on the far right, as x goes to 0, x squared goes to 0 as well. So now we have the limit trapped. Not only that, we know exactly what that limit is. So we know that as x approaches 0, x squared cosine 1 over x also approaches 0. Does anyone have any questions? I think we have one more.
Okay.
Here, let's get a broader picture of that. So we have x squared, we have negative x squared, we have x squared. Why is this brown?
I just don't like as x approaches 0, it's 0. I just don't like that.
Okay, so here's cosine 1, x squared cosine 1 over x. Kind of see like with the other one, you know, we might think just by looking at this graph, like, okay, it looks like it's flattening out, right? So notice that these oscillations do appear to be getting smaller and smaller, but the question is does it actually flatten out at 0, or is it, you know, like, what is it doing there, really?
Top and bottom just keep getting smaller.
Yeah. So, I mean, then something like this, you could keep zooming in, right, and you're still unsure. Is that 0? Is it like 0.000001? What is it, right?
Keep breaking it.
So then that's where this comes in. Like, okay, that's a weird function, but I know that it's in between this function and this function, both of which I know for sure touch 0, right? So zoom in a little more, and then we see that as, you know, we get off to these sides, whatever, it's symmetric, but when we see that what's taking place is now that we have it bound between these two functions, they're well behaved, they're smooth, approaching 0 like that. So we know that this thing has to be approaching 0 as well.
So basically, it's like a helpful like, visual proof of what we're doing with the equation.
Yeah, exactly. So what our graph there is just justification that this inequality is true.
This is pretty much the transverse product.
Um,
If A equals B and B equals C, then A equals C.
yeah, so that's
Pretty much the same thing.
kind of, yeah. But since we don't technically have equality here,
Right.
I mean,
It would be something different, but
it's kind of similar.
if A
Yeah,
and C
for
are the
sure.
same, B has to.
Yeah, I could see that making sense for sure. But yeah, so that's the idea. In the homework, they'll say, hey, here's this inequality, verify this inequality. I won't have you do this on the exam, so then they'll have like A, B, C, and D. I don't expect you to graph these kinds of things for the squeeze theorem. So when it says verify and choose the right graph, please feel free to just graph that on Desmos or something, because I'm not going to test you over graphing these types of things. Okay, so verify the inequality. I'm going to graph this function, and y equals 1. And then I can look at the graph and then choose the appropriate A, B, C, or D that they give me. Okay, so that's how you're going to verify. But again, on the exam, I would give you this inequality, for instance, and then I would say, based off based off of this inequality, what is the limit as x approaches 0 on sine x over x? Okay. So I give you the inequality, then I ask you what this limit is. And then so all we do is use this inequality to answer the question about the limit. So I've been given this inequality. I'll just insert the limit because that's what I want to know. I want to know what's the limit as x approaches 0 on this. And again, 1 minus x squared over 6, that would not be intuitive to come up with that. I know sine is in between 1 and -1, but you know, it's really, really ambiguous as to how that was even established. Luckily for us, it is already established. So what is the limit as x approaches 0 sine x over x? 1. So the limit as x approaches 0 here is 1 minus 0 squared over 6. And then the limit as x approaches 0 on a constant function 1 is the constant itself. Okay. So here's a limit as x approaches 0 on sine x over x. And we know that's in between 1, or sorry, less than or equal to 1, greater than or equal to 1. Therefore, we know that the limit as x approaches 0 on sine x over x is equal to 1. If those in values aren't the same, like if one was, I don't know, if this one was 1 and the other one was 10, then you're stuck. You've got to come up with a different inequality. So it wouldn't tell you any information unless those two numbers on the end are the same. Any questions on how that works? All right. And sort of the last kind of limit that shows up in 2.3 is limits on piecewise defined functions. So we'll look at a few of these. So there's our function. The first limit is the limit as x approaches 6 on f of x. So just like when you were in algebra dealing with piecewise functions, it really boiled down to which piece am I working with. It's the same with limits. If x is approaching 6, which piece do I work with?
Square root of x minus 1.
The bottom one, because 6 is larger than 1. So that's, well, okay, so that's the limit as x approaches 6 on the piece root x minus 1. So once we know where we're at as far as the domain of each piece, then we know which function to use. Okay. What about the limit as x approaches 0 on that function? Use the top function. 0 is smaller than or equal to 1. And that limit would be? 4. So the problems or the issues arise with piecewise functions, like we already stated in 2.2 when we were looking at graphs. The issue really arises in computing a limit that's approaching, in this example, 1. Like if I told you to approach 1 on this function, you see that there's two different pieces at 1. Right? So then you might say, well, I should probably use a one-sided limit if I'm approaching 1. If you wanted to see that more visually, I guess we could draw the domain of each one of these pieces out. Say that this domain is everything larger than 1, however you want to view that. And then the domain for the top piece is everything smaller than or equal to. So those numbers that show up in the function's domain, or if you're drawing a picture, those are the only values that, as x approaches, we need to be cautious of. So if I approach 6, 6 is completely contained within this. I can approach it from both sides without any issues. Same thing with 0. 0 is completely contained here. So when you're asked to compute the limit as x approaches 1, looking at those domains, you might say, well, I need to look at a one-sided limit here, because from the left is one piece, as I approach 1 from the right is a different piece. Is that clear? So to answer the question, what is the limit as x approaches 1 on that function, we really need to look at the one-sided limits. So as x approaches 1 from the right on the given function, what piece are we using and what is the limit?
We'd use the bottom piece.
Yeah, the bottom piece, because you have to approach 1 from the right. So I'm approaching 1 from the right-hand side. So I have to use this bottom piece. So this is the limit as x approaches 1 from the right on the square root of x minus 1. And that limit is 0. As I approach 1 from the left, we already talked about this graphically, but as I approach 1 from the left, I'm approaching this way, which means I have to use the function negative 2x plus 4 from the left. Is that hard to see, that color? So the limit here is
2.
2. Okay, so we've computed the limit from both sides of 1. What's the limit as x approaches 1? Does not exist. Why does it not exist?
Is it because the left side and the right side have to be the same?
Exactly, right. So the limit from the left and from the right have to be identical in order for the two-sided limit to exist. I'll just write it up here. So just take a shortcut. 1 does not equal to 2. Meaning this limit is not equal to this limit. Okay, so graphically, what does that tell us about the two pieces? They're separate pieces, right? They don't meet up at a single value. If they met up at a single value, then these one-sided limits would have the same value. Right? So you're looking at a graph that has a jump in it as x approaches 1 from the left and the right. You got different values here. This one's 2, and as we approach it from this way, from the right, it's 0. I don't know, whatever it looks like. We have two separate pieces. If they were connected, then we would know that as we approach from the left and the right, the y value is exactly the same. So on piecewise limits, when you look at the one-sided ones especially, and they're not the same, and it tells you that the two-sided limit doesn't exist, that will imply that your pieces are not connected. Wherever they are, they're not connected. Okay. Any questions about that? So that's how we look at those more analytically than graphically. If you have time on an exam or on a homework or something and you want to graph, then to make sure that you've computed the limits correctly, you can do that, but it's time consuming to do so. Okay, so the main cause for pausing and looking at a one-sided limit with any kind of piecewise function is if you're approaching either of these values. So if you were asked to compute the limit on that particular function as x approaches -3 or as x approaches 2, then you want to look at a two-sided or a one-sided limit rather. We know these things can get sort of elaborate. You can have 5 different values that it's separated. You have 5 different pieces. But these numbers that show up in the domain, you want to look at one-sided limits there. Does that make sense? Does anyone have any questions about this? No. And sort of not necessarily a piecewise function, but yet again another example of where one-sided limits are appropriate. If you think about the square root or any even root function, we always know that those have restricted domains. So if I said, well, let's look at both of these limits here. As x approaches 4 from the left and from the right, which one of those limits could we not compute? 4 from the left. Does everybody agree with that? So let's just say you forgot what that graph looks like. And this will kind of lead us into something we talk about in 2.5. If I'm approaching 4, as x approaches 4 from the right, let's say our 4 is here, and I'm approaching 4 from the right-hand side. Well, all of these values here are slightly larger than 4. So anything I plug in, if I'm thinking about this numerically for a moment, if I plug in anything that's larger than 4 and subtract off 4, that's a positive number. So I can take the square root of that. However, if I'm approaching 4 from the left, then I'm approaching or I'm plugging in or approaching through values that are slightly smaller than 4. So values smaller than 4, when subtracted from 4, give you a negative number. I mean, and you could see that numerically, even if you didn't remember what the graph of the square root of x minus 4 looks like. So the graph of square root of x minus 4 is the square root graph shifted where?
4 units to the right.
4 units to the right. So then naturally when you look at the graph, it totally makes sense, right? It's perfectly clear now. Okay, I can approach 4 from the right. but I can't approach 4 from the left because there's nothing over here. So this limit doesn't even make sense. So it's sort of in that way, it is kind of like a piecewise function in the sense that we have to look at one-sided limits. But really the point of that is you don't need the graph to do those. Okay. Does anyone have any questions? All right, so that's a good, well, yeah, that's a good spot to stop. Just a real quick show of hands, if we don't finish something in class, would you like me to upload the incomplete notes until we actually finish them so you can reference the incomplete notes? Like if we only got through half a section, do you still want me to upload the notes that we took in class?
Yeah, for sure.
Okay, I'll call those incomplete, just so if you reference them, or if you still see them up, I'll try to get rid of them once I upload the full version of the section, but I'll upload incomplete notes then. All right, let's take a break. Okay, this first page of 2.4 is really an overview of 2.4 and 2.5. So in 2.4 we're looking at infinite limits, and in 2.5 we're looking at limits at infinity. So right off the bat, we need to state that the limits in 2.4 that approach infinity, infinite limits, do not exist. So as we'll see, that even though we write they're approaching infinity or negative infinity, it's still not approaching a finite number. So a limit always has to be a finite number, just, you know, like any other limit in your life. It's some finite thing that you run up against. So they do not exist, even though we write, you know, them equal to positive or negative infinity. It's a little bit more descriptive than saying like in the piecewise sense that the limits don't exist, and then we looked at like one-sided limits. Here, anytime we write this limit is infinity or negative infinity, it means the limit doesn't exist, but it also gives us information about the function. So for example, here with what we have in this table in this graph, what we're computing is the limit, I guess technically the limit as x approaches 0 from the right on the function 1 over x squared. And just numerically, we're seeing that as x gets closer and closer to 0, the y values 1 over x squared get larger and larger. So in that sense, we would say that this limit is equal to infinity. But again, it doesn't mean there's a limit there. It just means as x gets closer and closer to 0, y grows without bound, is how we interpret that. And in fact, we can compute the limit from the left as well. And it's also infinity. You can see that graphically, not numerically, we don't have that. Well, I guess we do have plus minus, so either way. And so what that tells us about this function is, it could be misleading if we don't remember some algebra or pre-calc. The function 1 over x squared is not defined at 0. But remember, then there's two things we got to classify that as. Is that a whole or is it an asymptote? We've already seen how we know something's a whole. The factors on top and bottom go away. That gives us the whole. Here, the factor of x squared doesn't go away, so that gives us a vertical asymptote. So in fact, whenever we look at, let's see if we have space here. Whenever we compute these types of limits, so we'll say that, and we'll see this stated a little bit more specifically. So if the limit as x approaches a on any given function is positive or negative infinity, And again, what this limit is saying is that another way to think about it is, if we approach a finite number, well, if x approaches a finite number, and y, or f of x, approaches positive or negative infinity, then x equals to a is a vertical asymptote. Well, I have to abbreviate. So if you think about all the graphs that you've looked at that have vertical asymptotes, it's really the only thing that can happen. Right? We know what it is to have a vertical asymptote. The factor in the numerator and denominator don't divide out. So that's how you defined a vertical asymptote in algebra or pre-calc. They just said it's the zeros of the denominator that aren't zeros of the numerator. But in context of a limit, if you approach any finite number on any function and your y value is infinity or negative infinity, then you've got a vertical asymptote at that x location, at x equals to a. So that's what we're looking at in 2.4. Does anyone have any questions over that? I know it's really conceptual right now, but.
So if x approaches a infinite number from the left and the right, and then y approaches a finite number, then would we have a hole in that scenario? Or
Sorry, if x approaches infinity
So-
or negative infinity, you mean?
Yeah.
And y approaches a finite number?
Yes.
So if x approaches infinity or negative infinity, but y approaches a finite number, if we just take what we wrote here and just flip the x and y, what happens?
You have a horizontal asymptote.
Yeah, so it's not a hole. 'Cause we'll see that in a second, because x is getting arbitrarily large in this direction, and the function values are approaching something specific. So just if you were to draw that out, and in fact that's what 2.5 is all about. If x is approaching, way out here, and let's say this is our L that y is approaching. So it doesn't matter what it's doing out here, then eventually it approaches this L, and what that gives you is a horizontal asymptote. Yeah, but you're thinking about various scenarios, which is really good. And so that's a limit at infinity. When x approaches infinity or negative infinity, what does y approach? So that's limits at infinity versus infinite limits. So here's an example, numerically and graphically. The function 1 over x squared, instead of x approaching 0, now x is getting larger and larger in the positive direction. The y values are getting smaller and smaller. So here, as x approaches infinity, the y values are getting closer and closer to 0. So we'll just write as x approaches a positive or negative infinity. It's not always the case, but really we're saying that as this happens, what does f of x or y approach? So the more generic term for horizontal asymptotes that fits any function is end behavior. because not all functions have horizontal asymptotes, but all functions have behavior at the ends. You know, basically when you graph, where do the arrows go? So let's state that these limits the limits at infinity, that is. These limits describe a function's end behavior. And hopefully now end behavior makes a little bit more sense because you're computing the limit out here and the limit out here. What's happening on the ends? How does it behave at the end? Okay, in some senses, or some functions, you do have horizontal asymptotes. So what types of functions did we see involved a horizontal asymptote? What were those called? Or what's an example of one?
Rational function?
Yeah, a rational function, where we had like 1 over x, or x squared minus 2 over 3x plus 4, right? So rational functions. Just call it capital R of x. Rational functions have, at most, one horizontal asymptote. So for example, x squared minus 4 over, I don't know, whatever, x plus 3. Those functions. Sometimes those functions didn't have a horizontal asymptote. Sometimes they did. But if they do have a horizontal asymptote, they only have one. Remember, for like these kinds of functions, in particular, when they said find the horizontal asymptote, that is the exact same statement as saying, how does this function behave at its ends? So it's just that end behavior is a more broad phrase. Horizontal asymptote is specific to certain functions. Okay. So we've got to be able to like flow back and forth through that terminology because it's pretty much one and the same in the context of particular functions. Other functions have 2 horizontal asymptotes. So what's a function that you've seen that has 2 horizontal asymptotes?
Population growth?
So that would be, you would only have one there, like those logistic functions, like population growth, especially the population of limited growth, like a fish in a pond would only grow to a certain population before overcrowding takes place and then they start dying off. Right, so like, you know, maybe you start off with a couple of fish and then they reproduce and then they start filling up their environment and then they sort of level off. Yes, so like those limited population growth models do have 1 horizontal asymptote.
Well, sine and cosine.
The inverse.
Sine and cosine don't have horizontal asymptotes because sine and cosine don't flatten out.
Oh, right.
What's the square root of x look like?
Square root of x looks like that. Keeps growing slowly.
I was gonna say the inverse,
which would be, yeah, you're thinking about the graph of tangent, right? So if you think about the graph of tangent, tangent has vertical asymptotes, but then when we look at the inverse, vertical asymptotes turn into horizontal asymptotes, y equals x for an inverse, right? So the inverse tangent is an example that you all should have seen that does have two asymptotes, two horizontal asymptotes.
Right, which is x, right?
So, you know, the inverse tangent looked, oops, something like this. We have these two. That one straight? Good enough. So that was usually the, I guess, standard inverse tangent graph. You have two horizontal asymptotes at pi over 2 and negative pi over 2. Can a function have more than two horizontal asymptotes? Yes? No?
Yeah.
Yep, those are the options. 50-50, right? So just think about what we've just talked about. In the sense of a horizontal asymptote where you were kind of limited and you thought about it as, well, what's the degree of the numerator versus the degree of the denominator? That only fits with rational functions. So now with these limits, we're able to talk about if a function has horizontal asymptotes, we can find all of them because all we have to do is compute a limit as x approaches infinity and negative infinity, right? So in that regard, does a function have more than two horizontal asymptotes?
If we're looking at n behavior, it only has two n's, right?
Right.
So it can only have two asymptotes.
Exactly. So the maximum a function can have is two horizontal asymptotes because you have two ends at positive infinity and another one at negative infinity. So at most you can have two horizontal asymptotes for a function. You can have, I guess, maybe more, but it wouldn't be a function.
Would it be multiple on the same graph?
Like
Let's say, for example, another set of horizontal asymptotes. It's just a different, would it be a different function, or is that just pertaining to inverse tangent?
It could be a different function, and we'll see an example in this section in 2.5 rather, where you have a function that does this kind of thing. Or whatever, yeah. But that is like we'll see that function.
Okay.
But yeah. So if a function does have horizontal asymptotes, at most it can have is two, because again, the horizontal asymptotes are computed by the limit as x approaches infinity and as x approaches negative infinity. Okay. All right, that's about all I want to say about that for now. But that's the difference between these sections 2.4 and 2.5. Okay, infinite limits describe vertical asymptotes. Limit as you approach infinity describes end behavior. And if that end behavior is a finite number, then that is a horizontal asymptote. What's a function that doesn't have end behavior as a horizontal asymptote? Like trig functions, sine and cosine specifically? Yeah. We know tangent and all the others, we know that those have, all of those have vertical asymptotes. So really then, what we're asking is it ever possible, or can the limit as x approaches, let's say infinity, on some function equal to, let's be more specific and let's ask, can it ever equal infinity?
Yes,
Yeah, so what's an example of a function that does that?
x squared.
Yeah, like any polynomial function, right? So like the limit as x approaches infinity on x squared is infinity. But again, you're still talking about the end behavior. Remember when you were given a polynomial and they said, what's the end behavior of this polynomial? You looked at the leading term and said, well, is the coefficient positive or negative? And what's the degree, right? So since x squared is even and positive, we say that its end behavior looks like this, right? So this arrowhead is going off to infinity as x approaches infinity. And as x approaches negative infinity, the y values still approach infinity. So in that sense, we don't have a horizontal asymptote, but it still describes the end behavior of that function. Yeah?
Can you remind me what a cube root graph looks like? So x squared.
If it's positive, if there's a positive leading coefficient, cube roots look like this. So this is like, I don't know, this is like 2x to the fifth. If it's a negative coefficient, like negative 2x to the ninth in an odd degree, then they just get reflected. So yeah, that leading term test is what they call that. It's helpful. Because again, the more you can tie this stuff to prior knowledge, the easier it becomes to realize what exactly you're doing when you compute a limit. Okay, more on that when we get to 2.5 though. Okay, so that's the basic overview of 2.4 and 2.5, end behavior and vertical asymptotes. Okay, so this is, we're now back on 2.4. And the definition of an infinite limit is just as we discussed. So x is approaching some finite number on a given function, and the y values are getting larger and larger. That's how we interpret that. Or the other definition, x is approaching a finite number, and the y values are getting larger and larger, but in the negative direction. Okay. So in both cases, the limit does not exist. So you have to remember that a limit is always, if it exists, is a finite number in order for a limit to exist. Okay. So those are just some visual reinforcements here. We can still say that on functions like this, if the limit as x approaches a from the left on f of x is infinity, and the limit as x approaches a from the right on f of x is infinity, then we could say that one-sided limit is equal to infinity, but it doesn't really make that much sense because it's the situation that's happening is there's always that cut in your xy plane. So really in the sense of asymptotes, it only makes sense to describe the one-sided limits, and then you can infer from that, well, if I approach a from the left and the right, and they're both infinite, then I'm talking about a function that's doing that. But you still have to look at the one-sided limits in some cases. Or we could have the same situation, but the function value is approaching negative infinity from both sides. Or you can have any sort of combination of that. Do y'all have those figures, or are they on the next page? Whoa, what happened? I guess that's it. So there's other figures here, should have been. Because sometimes it just deletes
Yeah, I've got them on
stuff.
my page.
Yeah, think about it.
Okay. Yeah, I don't think I have them either. Oh, I do. Yeah. Lucky me. So then the discussion of these one-sided limits come up, and so the one-sided limits are specified, x larger than a, x less than a, right? But the same thing happens if I approach a from the left. I could go to positive or negative infinity depending on the function. As I approach from the right, I could go to positive or negative infinity. Really just depends on the function. Right, so you have all 4 of these scenarios spelled out. And all 4 scenarios you saw when you were graphing rational functions. So those are the 4 scenarios illustrated in those figures.
Scroll up a little bit.
Yeah. And is that good enough? So that's really what figures 2.26a, b, c, and d are describing. So that hopefully that's nothing new, especially if you remember graphing rational functions. You saw that time and time again when you graph those, that depending on the direction you approach a from or the vertical asymptote, it varied as to whether the function was going here or here.
I think one thing I'm kind of confused about, so if the limit is infinite, it does not exist.
Great.
Okay.
Yeah, these limits that describe vertical asymptotes are just that. Whenever you see a limit equal infinity, then you should default to say that's an asymptote there. There's a vertical asymptote there because the limit is infinity. Yeah. So then really what we want to talk about is not how to graph stuff, but how do we actually compute limits that are infinity or negative infinity. So if we look at this from like a pre-calculus or an algebra lens, that can be super helpful. So if I say, well, my function's 5 plus x over x, and algebra pre-calc, they would have said, what is the, are there any holes or asymptotes in this function? And how do you know which this function has? Right, so we first look at the domain. Let me just write. We first look at the domain of the function and say that x cannot be 0. Okay, so is that location in our domain an asymptote or a hole? An asymptote, how do you know?
There's no factor.
Right, there's nothing canceling out, like with those other limits we did in 2-3. The x doesn't divide out, right? Okay. Please don't make the mistake. I see this a lot. Hopefully it doesn't happen in this class. But this doesn't cancel with this. Like you gotta keep that straight. 5 plus x over x is 5 over x plus x over x. This simplifies to 5 over x plus 1. It's not just 5. All right, so hopefully none of you are in that habit, but if you are, then you gotta get out of it. Same thing, if it's like 5 plus x minus 5 or something like that, over x minus 5, these things don't just cancel out like that. If they're multiplied, then they cancel. I know that might seem like a very simple algebra thing, but I still see people in Calc 1 and sometimes in Calc 2 still do that.
So basically, if it's too easy, don't do it.
I don't know if that's a rule of thumb or not. I didn't remember if I started that or not. Just look at specifics. If you're not sure, just say I'm not sure about that. So what's 5 plus 3 divided by 3? If I do this, then 5 plus 3 over 3 should be 5, right?
No.
But 5 plus 3 over 3 is 8 over 3, not 5. So if I can't do that there, then I can't do that there. Maybe just simplify it numerically or something. Okay, so the domain is not including 0, and we know that x equals to 0 is a vertical asymptote. If you don't remember this stuff, it's probably good to review it. It can really help you out here. Okay, so I mean, that's kind of as far as we took it, right? And we would say, well, when I graph this function, I've got to determine what's happening over here and what's happening over here, right? And so we just plugged in numbers to do that. I already have one. Let me delete that. All right. Looking at that same function, in the sense of a calculus approach, you would see it as follows. You would see what's the limit as x approaches 0 from the right, and what's the limit as x approaches 0 from the left. So when you're presented with a limit like that, it's helpful to recognize, okay, this function, that factor of x doesn't go away, so I'm dealing with a vertical asymptote, right? So that's like, 90% of the battle right there. Now I know what I'm dealing with, so then it's a huge indicator as to what should happen to that limit, right? So we can sort of cheat, if you will, and just pull in previous knowledge to kind of guide us through these. But we are going to talk about how we just evaluate those things. So even if you just totally forgot about vertical asymptotes altogether, when you evaluate these things the way we do in calculus, it's going to tell you the same bit of information that we already know or should know by looking at that function. It has a vertical asymptote at x equals to 0. But if we just totally forgot that, we can compute this limit, or these two limits, and those limits will tell us that's the same information, assuming we remember how to interpret our limit. All right, we'll come back to that. So we defined what it means to have a limit at infinity, and then we can define the vertical asymptote in the sense of a limit at infinity. So if x approaches a finite number and the y values approach positive or negative infinity from both sides or from one side, then regardless of the one-side or two-sidedness of that limit, if the limit is positive or negative infinity, then the line x equals to a is a vertical asymptote. So that is the technical definition of a vertical asymptote. It's not the zeros of the denominator that are not zeros of the numerator. That is not a definition of a vertical asymptote. That's sort of a workaround before you have the language of limits. So this is the definition of a vertical asymptote. Questions? So if we had, let's just look at something a little bit more simply and say, I have something divided by something else in the sense of a limit. If this thing is equal to, let's say, infinity, maybe I won't use a and b since we're already using a. Let's say m and n. Or n and d for numerator and denominator. So if I compute a limit on specifically a quotient like this, and it's infinity, what has to be going on with n and m? So just think about what needs to happen in order for a quotient to keep getting bigger and bigger and bigger.
The numerator has to be less than the denominator.
So the numerator has to be less than the denominator. What do y'all think about that? In order for this to happen, the numerator is less than the denominator. So like if the numerator is, as far as a numerical value, if the numerator is 3 and the denominator is 10,
That's gonna get small.
yeah,
Then it's the opposite.
that's going to be getting smaller and smaller, right? So let's rearrange that. Well, sorry. Okay, the numerator is less than the denominator. It gets smaller and smaller. So, I mean, if you're thinking numerically, I think that's a good place to start. Like we're on the right track as far as like the quotient is getting larger and larger. What has to happen? I guess I'm looking for something like a little more specific. Remember, we're computing a limit too.
Numerator growing faster than the denominator's growing.
The-
One half the time you achieve different sets at some point.
Right. Okay. So that's perfectly valid. If the numerator is growing much more rapidly than the denominator, then that limit would be infinity. You what? Yeah, that's what like the y values of this n over m are approaching infinity, but we don't necessarily have to approach infinity. Like on a polynomial, that would be totally true, right? Like x squared. So I'll give you a hint. N is fixed or finite. And that might help. I guess the way I worded that was sort of ambiguous. But let's say the limit is infinity, but n is a finite number. In order for that quotient to be infinite, what has to happen?
M has to be arbitrarily small.
Smaller and smaller for the denominator, right? And if we go back to our first page, we can sort of see that. Well, I guess, yeah. So in order for, so like a quotient 1 over x squared, the numerator is fixed at 1, but what's happening to the denominator is that the denominator x is getting smaller and smaller. Therefore, 1 over x or 1 over x squared or whatever, the quotient gets larger and larger. So that's kind of what I was after. If n is fixed and finite, then, capital M. Then capital M is approaching 0. So in the context of like, a vertical asymptote with a rational function, we can say that I know that this is a vertical asymptote in this rational function because the denominator is approaching 0, right? And then that 0 is not going away by crossing out a factor up top. All right. So that's kind of the basis that we're working with. Did we go back to that other? Yeah, so we'll go back to this function specifically to look at how do we actually compute this. There's really not a standard notation for some of this stuff. Like if you look in the textbook, the author will just say, just write it out. The author is just explicitly writing out what happens. Other people might teach it differently. But I'll write it down and I'll tell you what I mean by it. Okay. So the idea here is we can typically with the vertical asymptote situation, there's nothing wrong with the numerator. Like we can plug the value that x is approaching into the numerator, and we get some fixed finite number out of that. But the problem here is that the denominator then is approaching 0. So we really have two options. That limit is either going to be positive infinity or negative infinity, right? We know that just from a pre-calc lens. 5 plus x over x has a vertical asymptote at x equal to 0. That's the limit they've asked me to compute. So again, that's like it's not that we're cheating, it's just that we're using stuff we already know to guide us, right? So these things are going to be infinite when you recognize you're approaching a vertical asymptote. The thing that we have to answer is, what is the sign? Is it positive infinity or is it negative infinity? And that depends on the values that we approach, the values that the denominator approaches 0 through. So there's the way, and if this notation doesn't work, then maybe you can think of it numerically. But the way I'm thinking of this is, okay, as x approaches 0, the numerator approaches what? 5. No issues there. As x approaches 0, the denominator is approaching 0. So let me just put this in quotes, because I'm not saying 5 divided by 0. I'm saying the denominator is approaching 0.
Would we say as it approaches 0, it's approaching infinity, right?
Yeah, so so then how do we know it's infinity, not negative infinity, is the question.
Because it's arbitrarily small, but it's positive.
Right, and it depends on sort of how we approach 0, right? So all of these boil down to, how are we approaching 0? Are we approaching 0 through positive numbers? Or are we approaching 0 through negative numbers, right? Since here we're approaching 0 from the right, those are all small and positive. So that's just my notation that I use to say that the denominator is approaching 0 through positive values. Is that acceptable? I mean, I could just write it out in words, but it's not a standard, like, agreed upon universal notation. It's just something that I've adopted. If you just want to write small positive number on the bottom, then you can write that. But that's what I mean when I write this here. Approaching 0 through positive values. I find it's really helpful to draw these like these pictures as references to do some of these limits, because it matters. The fact that the denominator is approaching 0 gives, and the numerator is fixed, that will always give me an infinite limit. But we have to reconcile the sign. What's the sign of the numerator and what's the sign of the denominator? Because I have to divide those things. So here, since I have a positive 5, dividing through by smaller and smaller positive numbers, then the outcome of this limit would be what? Positive infinity. It's kind of subtle at first. I've seen people do numerics where they'll plug in 0.01, 0.0001, and just see what the calculator gives them. But you've got to remember that no matter where you stop, the actual limit on this thing is going to keep going. Like if you stop at 10 to the negative 12 and your calculator outputs 10 to the negative 23, you don't write 10 to the negative 23. You write negative infinity. So you still have to have some bearing as to what you're doing.
But for the second one, even though it's approaching 0 or negative 3, would it be positive still?
Well, so you're approaching 0 from the left. So we're approaching 0 through these values. Are those values positive or negative? So the denominator is approaching 0 again, but it's approaching through negative values this time, because we're from the left or on the left of 0. Does everybody see that? Plug numbers into your calculator that are over here where our arrows are, and you can get a numeric sense. But again, this all I mean here is that the numerator is approaching 5, the denominator is approaching 0 through negative values. That means the quotient, we have 5 over a negative number that gets smaller and smaller and smaller, which means the quotient gets larger and larger and larger just because the zero's there on the bottom. But we have a positive 5 over a negative small number. So this is going to be negative infinity. So that's kind of how we're going to analyze those, or at least how I'm going to show you how to do that. If you want to look through the textbook, maybe numerical values or other videos, there's other ways to think about this. So if you can find something that works for you, by all means, utilize that. But we'll pick back up on Thursday.